Welcome to lecture 26. Here I'm going to talk about Huygens principle and the phenomenon of diffraction. Huygens was a Dutch physicist, Christian Huygens. Notice that it's Huygens, not Huygen, right? The S is part of his name. And here's what the principle says. This is a principle that's very useful for understanding how a wave spreads out, how a wave moves. It says the following. A wave moves exactly as if each point of a wave front acted like a point source, creating a spherical wavelet. So a wave front would be a line of constant phase. It's easiest to think of it as a wave crest, right? So you look at the ocean and there are all these wave crests, you draw lines along the wave crests, and the way these waves spread out is exactly as if each point on a wave crest acted like a point source, creating a wave going in all directions. That is not obvious, because the waves are not sort of going in all directions all the time. But I'll show you how that principle recreates what we know how waves spread out, and then we can apply it to something new, namely to explain this concept, this phenomenon called diffraction. Let's look at some simple examples first. So the first example I want to look at is the plane wave, right? And a plane wave is a wave where all the wave fronts, they're essentially straight lines, or if you're in 3 dimensions, sheets. So why they're called a plane wave. It's nothing to do with airplanes. It is not a plane wave, P-L-A-I-N, like a plain and simple wave. No, it's a wave where the wave fronts are flat planes, right? In the math sense of plane. So if you want to think of a specific example, imagine you're hovering sort of high above a beach and you watch the waves come in, right? A straight beach, no edges, nothing, just straight waves coming towards the beach. They're equally spaced apart. They're straight lines, right? Those lines along the crest of each wave. So let's ask what happens next. Now in this case it's very simple. We know what happens next. Each thing just moves to the right. But let's see how I can apply Huygens principle to reproduce that result. So I'll take each point on the wave crest, let's take the one in front, and I treat it like a spherical source, like a point source. Now of course I can't draw every single point on here because there's an infinite number of them, but I can maybe draw a number of them. It's like this. Like pretend I consider all those points as sources. What's going to happen? Well, this one, actually let me change colors for that. They each produce waves that spread outwards. So what's going to happen is that this one's going to create this wave after, a split second. This one has this one has this one, this one. The next one is, I suppose, this one here, then this one here. Of course, it should all look the same as I go from one to the other. I should have drawn them exactly at equal distances. I did my best. And like this. Right? So if you have all those simple waves interfere with each other, it's hard to do. Hard to calculate. There's lots of them. There's an infinite number of them. But what you're going to get is that they're going to, the sort of sideways motion is going to destructively interfere, so you don't get any overall sort of up or down motion of the wave. Like this part down here that's moving downwards is going to get cancelled out by some other source. But what doesn't get cancelled out are those bits here. So they create the next, if we spread out a little bit more, like this. I'm doing my best here to draw that. They're going to create the next plane, like wave front, like this. And of course this one does the same, so the whole wave again keeps moving. In this case it's not a necessary step to do to figure this out. We knew that anyway, but this is the way how Huygens principle gets us to the right result. Right? So all those single points create spherical wave. It is as if you like dropped a pebble right there and there and there at the same time. But the overall effect is a plane wave front moving sideways. Okay, let's look at another example. The second example I want to look at is a circular spherical wave, right? So imagine we're looking down onto a pond and I just dropped a pebble right in the middle. Now there's this wave that's spreading outwards. Where is it gonna go next? Well, we know what happened. It's just gonna spread out in a circle. It's gonna get bigger and bigger. But one way to reproduce this is with Huygens principle. I pretend each point on the wave crest is its own source. Again, I can't draw all of them because there's an infinite number of them. I can draw a few. And then each one of those is going to is acting like a source, producing its own waves like this, right? So like this one here produces a wave like this one like this one like this one like this. Get the idea. And then the overall effect I should draw this more carefully, obviously, but I'm lazy, right? Let me get the idea. They're going to spread out further, but after a little bit like this. I lost now which one I'm drawing. Really being very careful here. I spread out like this. You get the idea. There's each one creates a little circle that gets spreads out further and further and further. And again, they're going to interfere with each other, so there's nothing that actually goes like from this point goes this way. Like that part of the wave that travels this direction gets cancelled out by some other wave produced by one of the other tiny sources. But the overall effect is a new wave front here that spreads out like that. Again, the Huygens principle recovers the right result, even though here we knew what was going to happen, right? So this is really more a demonstration that this idea is plausible. Huygens principle makes sense. How do we justify Huygens principle? Like, why should it be true? I mean, I guess those two examples, assuming you believe that it does work out that way, which it does, right? I have no reason to lie to you. But even assuming you say, okay, fair enough, but why should that principle be true? Why should Huygens principle be true? Let me state this in just very briefly. So the justification for Huygens principle, it's the linearity of the wave equation. So the linearity of an equation, a differential equation, means that if I've got one function that's a solution, it's like physically allowed in the context of physics, and a second different function that's a solution, could be the same but general different function. The two functions both make this equation true, right? Remember the wave equation? Two functions make it true, so each function is a possibility, a physically possible situation. Then, because the equation is linear, there are no squares. There's the d, that's right on the wave equation. d2d dt squared is equal to the speed squared d2d dx squared. Right? Remember, this is in one dimension. Because the d appears here and here, it doesn't appear squared or log d or sine d, it just appears as d. You take derivatives, but it just appears as d. What it means is that if I have two solutions, d1 and d2, then d1 and d2 are together are also satisfying the wave equation. Right? So if I've got d1 that makes this true, this equation, I've got another solution for d that makes this true, well then I can add them together and that makes the equation still true. Which is wouldn't be the case if something was squared, right? 5 squared plus 4 squared is not 4 plus 5 squared, because there's a square in it. Here there's no square in it. Second derivative is not a square. It's just taking the derivative twice, not squaring the d ever. So this is the linearity property. There's a lot of powerful math that follows from linear equations. In fact, if you go on to study quantum mechanics, it's all about understanding the consequences of linearity. But one effect of linear equation is that if my wave, say this is my wave, this function here describes my wave. Of course, it should have x, y, whatnot. I'm just going to write like this. This is my wave. Right, this function describes my wave. I could write this as lots of little functions. d1, xt plus some d2, xt plus some d3, x of t, right? So at one point I'm saying, look, I'm going to decompose my wave into lots of tiny little functions that added up make up this one, right? And of course, for the purpose of Huygens principle, each one of those is like a single point in space. There's a spike. Like the water, this function says the water at this point here is high. This one says the water at this point here is this high. This one says the water at this point here is this high, right? So I add them up, and what they give me is, if I have a large number of them, maybe an infinite number of them, that my actual wave might maybe look something like this. This is my... Now I add all those spikes up, and I get this spike here, and this spike here, and this spike here, and this spike here, and this spike here. That's my overall function, so I build up like that. But then I can ask what happens to each one of those next, right? Because those together form a solution of the wave equation. It's a very hand-wavy justification of what is mathematically very well defined, right? And I don't expect you to master this idea based on the 2 minutes of just explaining it here, but hopefully it gives you the kind of mathematical idea behind this, right? That because there's no squares in here, I can write my solution as a sum, and then the sum itself so justifies the wave equation, so I can ask what happens to the individual parts making up the sum. Alright, so that is the justification for it, in a very hand-wavy, abbreviated manner. So now, let's see one new phenomenon that follows from all of that, namely diffraction. Okay, so here is the observation of the phenomenon that's called diffraction. Imagine I've got an ocean out here, and there's a harbor wall, and there's a gap in the harbor wall for the ships to go in and out. Like, oh, this side is the harbor. And the waves come in as essentially plane waves. And they hit the wall, and when they hit the wall, you know, they bounce off, maybe they splash around, so on. But then they pass through the gap. Now, on the other side of the gap, they don't continue just traveling sort of in a straight line, like between those two lines here, as if, you know, this straight line doesn't keep going in a straight line over, and up here and down there, there's nothing. Instead, what you observe is the waves spread out. And if you look carefully, you notice they don't just spread out in all directions. There's a fairly still water area here and down here. So if you park your boat here, if you're lucky enough to have a boat, I suppose, then this boat won't move much at all, whereas a boat over here will move up and down significantly. Of course, there isn't a simple sort of sharp cut-off, right? But the waves get smaller here and here. And so if you're right next to the wall, you'll sort of be protected from the incoming waves. Whereas if you're over here, even if you're not in a straight line from this, you're still going to be moving up and down. And if you compare this to another harbor wall with another gap in it, and say this gap is smaller, then the waves, what you'd observe is the waves, they spread out more. Right, so then the more narrow the gap means more spread. Let me write this down. So gap more narrow implies greater angle of spread. All right. So that's an observation, right, that we can make. I mean, this spreading out, that's fundamentally what we call diffraction. It happens to all waves, right? A similar effect is that if you just have one wall, there's not a gap. It's just there's this obstacle in the way, right? The waves will spread out around it. And one thing you'd observe there is the shorter the wavelength, the less they'd spread. Like longer wavelengths would spread better. So, in fact, that's an observation you can make. Longer wavelengths greater angle. course, I'm just stating this right now without proof. But let's agree that it is an observed effect, right? And it is, you know, an effect you know. Why? Because you can hear somebody talk around a corner. Why can you hear them talk around a corner? Well, because if they're talking over here, let's imagine these are sound waves rather than ocean waves, and you're standing here, then the sound waves will reach you even though they're not in your line of sight. Well, why can't you see them? Because the wavelength of light is a lot shorter, so the light doesn't spread out in the same way as sound. Right? So you can hear around corners but not see around corners because the wavelength of sound is a lot greater than the wavelength of light. Right? So the wavelength of, say, somebody talking, the voice, is approximately 1 meter, depending how, you know, high or low they talk. Like 1 meter would be 340 hertz, which is, you know, it's somewhere slightly above, I suppose, the E above the middle C here on the piano. So fairly in the middle of a sort of lowish female voice, the high end maybe of the male voice. So 1 meter, slightly more, slightly less, doesn't matter. Whereas the wavelength of visible light, I'm sure it's a different wave, but that doesn't change how this principle works, is about 500 nanometers. You know, 300 to 700, something like that. So this is 1/2 millionth of this. And so, given these observations, you might have determined those experimentally, the light will not spread out very much at all. You'd be hardly notice at all that it does spread out. So really you say you have to be in line of sight, meaning in a straight line. Whereas hearing sound, say somebody talk over here, creating these sound waves, well, that sound spreads out. Now, of course, you can also hear them a little bit if they're right here, but that's because, well, the wall itself is going to carry some of the sound. The sound might bounce off somewhere else, and so on. So this is a bit of an idealized picture. Can we think of an example where there are electromagnetic waves, such as light, where we can get diffraction? Yes, for example, with radio waves. So let's take not radio, let's take maybe your cell phone reception. Cell phone reception is something like 1,000 megahertz. You know, maybe I think 800 is a common frequency, or just under 2,000, something like that. So that around the 1,000 megahertz or the 1 gigahertz range. So you can do the math. Speed of light, right? 300 million meters per second, 1,000 million hertz. So the wavelength of say cell phones is about 30 centimeters, which is much closer to the wavelength of sound coincidentally, right? So sort of high-ish sound, like a high female voice, maybe might have about the same, or you know, maybe singing, a soprano might have about the same wavelength as the electromagnetic waves that your cell phone uses to get reception and to communicate with some cell tower somewhere. So those waves would spread out equally. And if you have a say if you have some kind of mountainscape, right, maybe like this, then, and there's a cell tower over here sending, you know, those waves, if you're here, you might not get reception. Why? Because the waves they get here and they spread out, just not enough. Right, so you're sort of in the shadow of the mountain. Whereas if you're down here, you might get it, because even though you're still not in a line of sight with this one, because light, like visible light, doesn't spread out enough. There's not a straight line passes through a mountain. These waves, they spread out enough that they might reach this point. So the fact that you can get cell phone behind a mountain, just not directly in the shadow of a steep cliff, for example. And the fact that you can hear around corners are example of diffraction at work. Okay, so this was an observation, but how does Huygens principle explain it? Well, let me just stick with this picture here. If I imagine the wavefront right here, right, and I draw all those points, I earlier used green for that, I pretend each of those points is a source, then those spreading out like this, they will sort of cancel the sideways motion here, but the ones that the waves created in this way by the point sources, right, they don't get cancelled out, except if you try to go very much straight up, then there's another point further down. Say this point here, the wave has moved on a bit, and this point here and this point here, like this point here might interfere destructively with this point here up here, but not over there. Right? And if the gap is more narrow, then there's sort of less room for those two, say, to be half a wavelength apart. Right? If this is half a wavelength apart from top to bottom, then those 2 points will just exactly interfere destructively going up in a straight line. Right? But so all the others would still contribute. So you'd see a little bit wave here. Whereas if you've got, say, multiple wavelengths of width, then there's going to be enough destructive interference between this. Say this one interferes destructively with this one in this direction here, and this one interferes destructively with this one in the same direction, so you get very little wave up here. Whereas going forward, the distances from those points are closer to each other, so there's no point here where you find perfectly destructive interference. You can do this more mathematically to actually find the angle, and you can talk about it in class. But what's important for the purposes of what we'll be doing next is really just to understand the basic idea of diffraction. And how I can explain it by looking at little point sources. Well, each one wants to spread out, so they're going to spread out upwards and downwards. They don't care that they originally were a chunk of a longer wavefront. Right, this point doesn't care that earlier on there was more on this side of it that then hit the wall and disappeared. At this point does what it does, and it spreads out. And we'll be using Huygens principle in more detail in a situation like this to analyze this in the context of what's called a single slit experiment or single slit diffraction, which, as it turns out, this interference of this point with this point with this point with this point, yes, part of it is that you get destructive interference up here and down here, more so than over here, because the path distances are more extreme here. But also, if you keep going far enough over, you're going to get that there are maxima and minima over here based on the interference of those individual points, and that's called single slit diffraction, the single slit diffraction pattern that we get. We'll talk about that in a future video and possibly in class.